Ramakrishnan is a Lonergan Professor Emeritus of Mathematics at Caltech. Dinakar received his PhD from Columbia University in 1980. His research interests include number theory, representation theory, arithmetic geometry, and even mathematical biology. From 1986 to 1990, Dinakar was a Sloan Research Fellow. He's been a Fellow of the American Mathematical Society since 2013. And today he's going to be telling us about an invitation to Diophantine equations, congruent numbers, and beyond.
Right. Thank you very much for the invitation. It's been a pleasure to be here. This is my first visit to this university, in fact, to Denton. And in fact, it's only the 5th day I've spent in Texas in my life. So, yeah, it's nice to be here. So, thank you. And, all right. So, I thought I would talk about Diophantine equations. And I will tell you what they are. And you're welcome to ask me questions. But sometimes I may say, okay, maybe we'll talk later because it gets complicated. Because it depends on the length of the answer. I can give you a quick answer, yes. But anyway, all right. So, as you know, first of all, I should say here that the most basic objects, I work with number theory, and the nice thing I like about it is it has a lot of old, deep history. Been studied for a long time, not just in one place, in various places in the world. And so it's very natural. So, the question is, what is a Diophantine equation? Well, it was studied and written about by a man called Diophantus. And so he lived actually in a place called Alexandria in Egypt. That much we know, but we don't actually know exactly, so maybe I should say now Egypt, because for a long time it also belonged to the Greeks. The Greeks controlled it, and then the Romans controlled it, so there were a lot of things here. And it's named after, actually, Alexander the Great, actually. And, but we don't know exactly, so maybe he did do one thing I will mention later, that he did several things, but anyway. So, we don't know exactly, we don't even know if he was a Greek or whether he was an Egyptian or he was something else, we don't know. Actually, so it's a good thing if you like history of math to actually try to learn about him. I think very little is known, so it's very interesting. So anyway, his idea was to look at equations, essentially something like this. So he studied equations here, which are polynomial equations with uniform coefficients. Sorry, this is I apologize ahead of time for my handwriting, which may not be good. With coefficients in the integers. See, if you know the integers, for me it's very straightforward, etc. And goes on and goes to infinity. And one can spend a lot of time just defining the integers, so I'm not going to do that. And there are some very basic axioms called the piano axioms, and we will accept that in this thing, including induction, because that's kind of, so I guess it's not exactly first order, because we allow induction, but I won't spend too much time on it. And so, does anybody know why it's called Z, the integers? Oh, yes?
Solid.
Yeah. Stands for Stalin. Z is pronounced like TS. Okay. All right. So, and I will also look inside the natural numbers. So many of us, for natural numbers, especially in the Anglophonic world, natural numbers are like this. is a contradiction, but to them positive number includes 0 as well. Okay, so anyway, so you have coefficients in Z, and then, so this will be polynomial equation in a bunch of variables, x1, x2, up to xn. So, and then what we want to do, this is a basic problem. So by the way, it need not be just one equation, it could be a system of equations. And that is sometimes called the Diophantine system. But I'll give you some very simple examples. So what are the major problem? The main problem is to, I'll give you examples very soon. So is to look for solutions in integers in Z. So i.e. you want to find some whatever x1, xn, each of them in Z, such that the polynomial, the equations are satisfied. And actually in the old days, classically, people didn't allow Z. In fact, many people in the West actually didn't know about 0 actually. So, but they would often only look for positive integer solutions. So that's why I introduced this. They often look for solutions in n. And okay, and so this is quite important to do this. And this is actually turns out to be very difficult. And it's kind of difficult in a very complicated way, in that, first of all, it's very hard to find solutions. That's good. Second thing is that it's very hard to even prove that there are solutions. Sometimes in math you can prove that there are solutions, but then you don't know how to find them. Okay, so that's the second level of difficulty. And the third level of difficulty is there is not even an algorithm to determine if there is a solution. So therefore it's very difficult in general to solve them. So therefore what people do is, of course, is to try to solve, special classes of equations. Special classes of equations which are called Diophantine equations. And I will start talking about them very soon, right now. But before I go on, I want to tell you that given a polynomial equation, for example, the easiest solution equation will be something like this: x1 plus x2 up to xn equals 0. So you could have something like this, or maybe some constant here. And then you could try to solve it. And then we know how to solve these things very well if you work with real numbers. So many people are familiar with these equations, and they'll try to find real solutions. So here my C is going to be an integer also. And then if you know something about complex numbers, you can also look for solutions in complex numbers. And many times the difficulty is not understood when you go to the real or complex numbers, because the equations, it may be very, very hard, next to impossible, to find the integer solutions, but then you can easily find the real solutions. Sometimes if you don't find real solutions, you can always find complex solutions. So therefore, if you take here, if I write x here, the set of solutions in, if you like, in natural numbers, this is actually sitting inside x of z, which are a set of all the integer solutions, and that's sitting inside the real solution, and then it's sitting inside the complex solution. What is really interesting is that the real or the complex solutions imply something about whether you'll find solutions in Z or not. So that's kind of very surprising. So, in a sense, the complex solutions may be something like this. I'm not good at drawing, but something like that. And the real solution may be something like this, you know. And then the rational solutions may be, yeah, maybe I should also say, you can also look here at rational solutions. And Q are the rational solutions. So Q is the rational numbers. So it'd be like A over B, where A and B are integers and B is non-zero. You know why it's called Q? Quotients. Yeah, you're right. It's a quotient of integers. So I like to think of this way, and then inside it you have the so rational solutions are like this. Inside the real solutions, and then you may have some special things, maybe the integral solutions. So anyway, you can always think of what we are looking for as sitting inside something. So it could happen that this set X of Z is empty, no solutions, but then you still have something here. And so that's really what we want to look at. By the way, it's a complex solutions are going to be, it's be like one, you know, like I'm drawing it so that it's a complex one-dimensional in this example. But complex one-dimensional is real two-dimensional, and I can't really draw it on the board, so I'm only drawing what is called a section of that. I try to make it look like it's three-dimensional, but no, it's fitting inside. But it's hard. Okay, so all this is very general, nothing in here. And as I said, the first recurring theme is that this is one thing that I like, and I want to come back to this. So the recurring theme is the geometry of the real or complex. Actually, in some sense, the complex ones, even more than the real, for a reason I will explain in a second, plays a role, implies something deep about the unitary solutions, or I'll just say X. So, by the way, this is a term that mathematicians use. Deep means for us that something that is not easy, like really hard, and you have to go deep into it to analyze it. But I've found that with non-mathematicians, they don't understand this at all. Because when I say it's deep, what do you mean deep? Like, it's not deep. They imagine some well. It's not like that. This well is in your brain. Okay. But anyway, I will use that very often. So that's the first recurring thing. So maybe I should say one here. And the second recurring theme, two, is that a necessary condition to find an integral solution is to find solutions modulo, I will explain in a minute, some fixed integers m for all n. So these are sometimes called, these lead to something called congruences. I'm assuming you've all seen congruences, right? Alright, so, okay, if not, I can explain, it's just, maybe I'll just, again, I'm not giving you any example yet, I will very soon, but I wanted to say first, these are the two recurring themes. Somehow the geometry that you have in the real or complex numbers tells you, puts conditions on the integral points, and secondly, you need to have solutions modulo n. Okay, so what are congruences? So congruences are like, so if you're given, suppose, some polynomial equation, f of x1 with xn equals 0, coefficient. For example, we looked at before, f of x could be, I write x for the n tuple sometimes, something like this. Maybe something like this. So this is a simple example. So what we can do first is that we can look, or maybe I should say for every whole number m, look at the congruence, which is this modulo 0, modulo m, 0 modulo m. So what does this really mean? It means that i.e. integers, let's say b1, b2, bn, such that f of b1 to bn is divisible by n. So may not be 0, but it's going to be divisible by n. So it's clear that if you have a solution, integral solution for f, then you must have a solution mod m for any n. So the question you can ask right away is then, can we go back? So if we have solutions for congruences mod m for all m, of course, then is there an integral solution? It's actually not a trivial question at all. So I should tell you that when I was starting out, when I was a student like you, when I asked somebody this question when I was taking my first course in number theory, and they gave there exist counterexamples. You all know what a counterexample is, right? So, and there's a famous one due to Selmer, and then he said that if you take this equation, 3x cubed plus 4y cubed plus 5z cubed equals 0, then he showed that this has no solution in positive in natural numbers. Of course, there's a 0 as a solution, 0, 0, 0, but it's not very interesting. So there's no solution in, if you like, n cubed here, but it has a solution modulo m. By the way, when you want to look at solutions mod m for all m, it's in effect equivalent to looking for solutions modulo all prime powers, because you can factor these. But anyway, he proved that you can use these results to prove that there is a solution mod m for every m. So when I see 0 solution here, I mean an n cubed, right, non-zero. So this is actually not easy. It took me a long time to check this when I was a student. I wrote a project report about this because it wasn't easy. But then, but I felt really stupid when maybe like just 10 years ago or maybe less, I learned this very elementary counterexample. This means there exists, right? No? Okay. Elementary counterexample. This, by the way, this is very important because this leads to a lot of interesting questions about things called elliptic curves, which is really at the center of a lot of things about number theory and algebraic geometry. So it's really, really important. But just to answer this question, there is a really simple counter example due to Dawkinson. It's so elementary that it's kind of embarrassing if anybody thinks about it. So he said, consider this equation. Look at f of x, y, I don't know, z, w, let's say 4 variable. I should write x1, x2, x3, x4, but this is okay. So then you just take this guy here, you take x squared plus y squared plus z squared plus w squared plus 1. Right? This has no solution. Has no solution in z. There's no solution in n or whatever, 4 or z to the 4th, even, but now, in fact, even over r to the 4th, it has no solution. But now let's look at mod n. But now mod any m greater than or equal to 2. This thing to be 0 is the same as x squared plus y squared. By the way, it's clear, right? Because these things are all positive. This is non-negative. You can't add a plus 1 and make it 0. Right? You're looking at this as 0. So now, then when I take this here, equals w squared equals minus 1, except now I can write it as m minus 1. So anyway, so you can check that this has a solution, because it has a solution in, anyway. So you can think about this, right? So actually mod m. So in fact, you can put any multiple of k here. Then you see from this that there is a solution. So there is a solution mod m for every n, but no integral solution. By the way, but I should say that Selmer's solution is still finer than this one. Why? Because this thing here doesn't have any real solution either. Right? If you take x, y, z, w, you put any real number, there is no solution. So this thing here, so this equation has no solution even in R4. Because the sum of squares, again, it's non-negative, it has nothing to do with integers, and this plus 1 cannot be 0. Whereas this thing here, Selmer's thing, it has a real solution as well. It has a real solution. So it's actually better. So it turns out that if you have a real solution, and then if you have all the congruent solution, so you can ask, maybe then you can have an integral solution. So there is a very famous theorem of Hasse, and he said that if you have a quadratic form, so I'm kind of jumping the gun because the first equation is to consider the Diophantine equations or linear equations. I will tell you about it in a minute, because that's the only case we can really solve completely. And then, well, quadratic almost. And Hasse proved for quadratic, so if you have a quadratic equation, so you have f, so if f is a quadratic form, so that means that every term, whenever people say form, that means the degree of each term is the same. Here. And then if you have a quadratic form in any number of variables with real solutions and all the, let's say, congruent solutions. So essentially what he proved also for powers, and then it has a rational solution. So it's a very beautiful result. So see the congruence mod M can be always split up into congruence modulo the prime powers that divide M. So essentially, if you know how to solve them modulo all the prime powers, then you know mod M. And then if you fix a prime, so it really becomes prime by prime, you analyze what happens, whether there are solutions. And if you're given prime powers, and if you have solutions modulo some fixed p, power of p, then you can look for solutions for all modulo all powers of p, and then it leads to what is called p-adic numbers, which are very important. And just like they're like real numbers, as far as the number theorist is concerned, the p-adic numbers are as important as the real numbers. They're all kind of different facets of the same thing. So anyway, so I won't state it very precisely, but Hasse proved this really beautiful theorem. Okay, so do I want to? What time did I start exactly? I'm trying to.
5:02.
Yeah. Okay, I won't spend time on this, but let me just say here that linear Diophantine equations can be solved in the sense when they can be solved. So that's what I mean. I mean, if there is a solution. And it is, in effect, linear algebra. So I should say, if anybody is interested, I can tell you later. But it turns out that, by the way, linear Diophantine equations are very important. In fact, this is what I learned when I tried to learn some chemistry. When you study chemistry and look at a chemical equation, they try to balance the equation. And it's really just solving linear Diophantine equations. So I showed, this is how I started learning this field, because this person said, oh, this is complicated. I looked in this book, they use some formula. But I said, no, I can solve very general. It's not often a mathematician finds something he or she can solve for a non-mathematician. So he thought I was a genius, but I said, not quite, it's just linear algebra. But it's actually very interesting to do it. Okay, but so I won't say too much about linear case. Okay, so maybe I should, maybe I'll say a little bit about the very basic equations. So anyway, we've analyzed one theme of this congruence mod M, etc. Yeah, maybe I should have said that first, that I talked about congruences having solutions, but very often congruences do tell you there is no solution very quickly, right? I mean, it's, I don't know how to say it. For example, maybe I should have given this first. Something like x squared plus 3y squared equals 8, right? Does it have a solution mod in integers? So you reduce mod 3, and it's mod 3, what happens? So then this term drops out, and you just get x squared is congruent to 8, but 8 is congruent to 2 mod 3. And then you see that there is no number mod 3. Mod 3, you just have 0, 1, 2. If you square them, you never get 2 mod, right? So this means that there is no solution here. No solution mod 3. So it's very good in that if you have no solutions, then you are in good shape. The bad thing is, of course, when you have solutions mod everything, then you can't say anything. It's kind of like if you don't do your homework, you don't do well in the finals, but if you do all the homework, there's no guarantee of doing well. Life is asymmetrical. Okay. All right. Okay. So. Okay. Oh yeah. So maybe I should say something. A few things historical. So Pythagoras' theorem. I will try to so this theorem, of course, says the right triangle. I have a bad habit. All my triangles look like they're isosceles, but they're not. Okay, so if you have x and y and this is z, then you have the equation z squared equals x squared equals y squared. Alright, so this is Pythagoras' theorem. And the question, of course, is, so we have lots of them. They happen all the time. Every time you go to the building, you see right triangles everywhere. But they're not measuring integral lengths. They don't care. It's some real number. So this thing here is stupid to solve. Lots of solutions in R3. And so the question is, what about integral solutions? Are there positive integers, x, y, z, where you can find this thing? And then when you have an a, b, c positive integers, with, let's say, a squared plus b squared equals c squared, is called the Pythagorean triple. So I should say that Pythagoras, long before Pythagoras, this problem was studied long before, I'll just call him P, Mr. P, in various ancient civilizations. Like Babylon and China, India, and a lot of places. I'm not giving you many places to study, and they really wrote down. So of course, 3, 4, 5. Anybody can write this, but Babylonians, for example, they wrote down this 3, 3, 6, 7, 3, 4, 5, 6, 4, 8, 2, 5. Very nice solution. It's nice that they had it. If you just try to square it with the technology they had, it was pretty amazing that they did it. And actually, this was one of the things that was in a clay tablet. And for many of you who weren't born when Saddam Hussein was in Iraq, so the clay tablet was in a museum in Baghdad. And so when he was deposed, this disappeared for a while, clay tablet. But finally they located it and put it back in the museum, so it's kind of interesting. So, okay, so I think it is very, very interesting to study these things. And the point is, what did the Greeks do? Why do we mention Diophantus and Pythagoras and all these people? To me, the reason is, all these people in all these countries, when they would see a problem, they would solve it. They would try to solve it, and then if they found a solution, they would try and find another solution, and then go on for a while. And so sometimes, I think, like some writings from India, which I read, are very interesting because they say, and so on. But, come on, you can't tell after the first 4 solutions, or first 10, how to go on. So I think the Greeks, what they did, I think that's why I consider Greeks kind of like the beginning of modern number theory, in that they wrote down proofs of everything. They would, they emphasized writing proofs and also finding a formula and explaining what it is. So anyway, and I wanted to bring in also this other, maybe I can just write here. So as I said, the real solutions are very important as well as the complex solutions. So for example here, I could change variables and you look at u equals x over z and v equals y over z. Then I get the equation u squared plus v squared equals 1. So the idea is that suppose you solve this equation for u and v, which are rational. denominators and get integral solutions. So therefore, it's actually very reasonable to look for rational solutions of this equation star. I'm mentioning this for a reason, because this is the first example of what I told you before of recurring theme 1 about the geometry. We all know how to, hopefully it's okay to, so if you look at the real plane, the UV plane, u squared plus v squared equals 1 is going to be a circle. So the real solutions are circles. So there are lots of solutions, infinitely many solutions. In fact, there are uncountably many real solutions. So you have these things here. But now, I want to find all the solutions which are rational numbers, which coordinates are rational. And here comes the real big rub I have about the way we teach math. And we always say, oh, this is really good. And you know, every point here you have two coordinates, cosine theta and sine theta. And this is cosine theta and this is theta. And then this is so, but for us number theorists, this is not at all a good parameterization. Because how in the world, I was going to say how in something else, but how in the world do we ever tell that cosine theta or sine theta is rational? Okay, if you're really smart, you can, but it's actually hard. So this is not the way we want to do it. We don't want to parameterize it using the usual parameterization. So what people did, whoever did first, I've been trying to find out who wrote this solution first, but I haven't seen it. So one of the solutions, so there are two natural solutions. One is here, where x is minus 1 and y is 0, right? This point is very, very important. That's certainly one of the Pythagorean triples that gives you, because u equals minus 1 and v equals 0. So now what you can do is that you can actually draw from there rays emanating from this point into here. And how can I make sure that the rays I choose, this point here has rational coordinates? What should I do? What do you think? The slope, who said that? Okay. Okay, thank you. That's right. So because this is a rational point, and if the slope was rational, then this point also would be rational. So that's the way you produce. So in fact, conversely, if you start with a rational point and connect this point to that, the line would have rational slope because these both are rational points. So actually, therefore, all the rational points except this one are going to be obtained this way. So you can actually add all of them, and you also can see very easily there are infinitely many. But it's more than that. So the right parameterization for a point on a circle is not this, which is a loser. So instead you should look at solutions which look like this. You want something using rational functions. So this is like 2t over 1 plus t squared, 1 minus t squared over 1 plus t squared, where t is a parameter. T is called a parameter. So using that, you get all the rational things this way. I just wanted to say, so again, use the geometry of the real points. So you know what to look for. You exploit the geometry. But on the other hand, you're not satisfied with the real points because you want rational points, and then you do that. So it's very, very good. In fact, I should also say something about the solutions of Diophantine equations. If you take x, y, z, by the way, suppose you have a solution like a Pythagorean triple, ABC. Yeah, maybe I'll. Now, this ABC, if I can produce another one in a stupid way. I can just multiply this by some n, NA, NB, NC. Then it'll give me another solution. So anytime you have a homogeneous equation, you can always produce a So these m and n will be integers, 2mn times then m squared minus n squared, m squared plus n squared. This comes from this here, so here you have 2t over 1 plus t squared. T is a rational number, so you can write it as m over n. That's what leads to these things. But to have the primitive ones, all you have to do is you have to take m to be greater than n, and then m and n are relatively prime. So there will be nothing in common. So it's a very beautiful thing. I still like it, even though it's very elementary. I still enjoy. I enjoyed teaching my son when he thought I made a trick, and he wouldn't believe it for some days. But when he was in high school, or maybe entering college, whatever. So. Okay, so of course this recurring thing gets much harder because, alright, okay, I'm not going very far, but I do want to say something about Diophantine. So if you look at, for example, the other x squared plus y squared plus z squared equals n, so Diophantine was very interested in this equation. I don't know why. I saw this. By the way, I didn't read the original thing, whatever that is, but I read it in Latin. You can buy it, I think it's also available in French, but I don't know if there's any other. But how many of you know Latin? None? It's one of my favorite things. Latin is so beautiful. Okay, all right. So, in fact, when I was a grad student, I had to take 2 foreign languages, and I took Latin as one of them. And the department refused me first. And they said, why? And they said, well, you have to produce deep, relevant mathematics in Latin. I showed them these books by Euler and Fermat, and they were all written in Latin. In fact, Gauss also wrote everything in Latin. And he was actually very unhappy with his student Riemann, who was not a bad mathematician, because he wouldn't write in Latin and he wrote in German. Riemann, I think, was the first one, kind of, who really wrote in German. So the people who wrote in German, actually, it was only 100 years. Whereas before that, for several hundred years, they wrote in Latin. Okay, anyway, too much about languages. So what Diophantine said was, okay, he was very interested, which integers can be sum of 3 squares? He never wrote it down, but I have a feeling he knew that every integer is the sum of 4 squares. This is a famous theorem. But I get the feeling that he knew. Because he was really looking at 3 and he was saying essentially, it's not trivial, 3 is very hard, etc. So he analyzed this, so he looked at the case n equals 10. So he showed that the solution x, y, z, so this thing here, there is this solution, x, y, z is equal to, so he was looking at rational, but he was looking for rational solutions. But anytime you have a rational, anyway, so it's not true that, so this is 1285, and then 1288. He found this solution. It's really neat. It's not trivial to find this. As an exercise, you can try to check that it's a solution, but how did he come to it? It's a miracle. That's actually, reading Diophantine, to me, I was always intrigued by this Indian mathematician Ramanujan. I could never understand why he came up with all the things he did. It seemed like magic. He just said, oh, this is true, obviously. It's not obvious to me. And I think reading Diophantine is kind of a little precursor to it. He also doesn't explain anything. He just writes down. He says, okay. So I think it's really great. So it's a great solution. But I should say that in 1798, Legendre, this famous French mathematician Legendre showed that the only integers, the only n which are not sum of three squares, the only n's which are not sum of three squares are of the form, maybe I should say only integers, positive integers, which are not sum of three squares, are of the form n equals 4 to the a times 8b plus 7. That's it, with a and b positive. Of course, 10 is not of that form. But it's kind of a very beautiful result. So it's much more beautiful than saying that every integer is the sum of 4 squares. But the sum of 2 squares also people, Gauss gave complete results for sums of 2 squares. But it is clear that people have thought about this before. He wasn't the first one to look at it. So I think Gauss was also influenced by old works, but except that he was so smart he completely solved it. Okay, so maybe is it too much history? Okay, I kind of like it. So, all right. So maybe I should say something about Fermat's last theorem. And then he said that if you look at f to the n plus y to the n equals z to the n, for n equals 2, of course, this is Pythagorean triple problem. And he said that this has no. So now, if n is greater than or equal to 3, he said this has no positive integral solutions. And of course, this is called Fermat's last theorem because he said infamously that the margin was too narrow for him to write a proof. But actually, my son had an interesting suggestion. He said in the textbooks they should have Fermat's statement, the margin is too small. But then you should say, was it? And then on the margin, you should have a link. You click on it, and it goes to the proof of Andrew Wiles. So, it's just that his point was margin is not well defined. Okay. Okay. So anyway, the point is that the reason it's called by Fermat's name is that Fermat did show this for n equals 4. In fact, he showed that even this equation x to the 4th plus y to the 4th equals z squared has no such solution, positive integer solution. And most important reason I think it's important, what he did is he introduced a very basic concept called the principle of infinite descent. The idea is very simple. If you have a solution in positive integers, you do something to it and try to find a solution that's smaller than it in positive integers. And then you go on like that, then you call it infinite descent. But in fact, there is no infinite descent because once you start with positive integers, if you believe in, as I said, I believe in induction, which is equivalent to what is called well ordering, which says that if you have any collection of positive integers, there is the smallest one. So he introduced the principle of infinite descent. So he really was very important because it's used all the time in number theory, even these days. So he did that. And of course, you all know that Andrew Wiles proved this in general, but before I mention his result, I should make a remark that there was a very interesting result before Andrew Wiles proved it. So there was I don't remember the exact year, I'm sorry. I want to mention this Sophie Germain. She said, suppose P is a prime and 2P plus 1 is also a prime. Then she said, by the way, Fermat's last theorem could be reduced easily to, because it's known for n equals 4, it's enough to prove that for n a prime number. Because, so, then she showed that x to the p plus y to the p equals z to the p implies p divides xyz. That means if p doesn't divide xyz, there is no solution. So that's sometimes called the first case. It's a very interesting argument and very interesting. And the point is, I want to tell you, so of course, if you take p equals 5 or 11, etc., many primes you can find where p and 2p plus 1 are primes. But it's an open problem is to know, are there infinitely many Sophie Germain primes? It's unknown. It's amazing that it's not known. So anyway, so of course there's a famous theorem, and Wiles where he proved Fermat's last theorem is true. There's no way I should say the blackboard is not big enough for me. Okay. This theorem holds. It's true. Okay. In some sense, somebody said they should say Fermat's last theorem is false because Fermat claimed this as his theorem. That wasn't true. But you know what I mean. It's true means that. But so he used results. He used essentially what I would call important. I won't say anything about it. Modular forms and what I call Galois representations. I will just write down the buzzwords. So these two things are very important and they are linked, and a lot of modern mathematics people do these things. And also he used results of Ken Rivet, very important result, and also I'm going to put it this way, a result of Taylor and Wiles. Taylor was a student, Richard Taylor. So, okay. I won't say anything about this, but I want to tell you, how much time do we have? 5?
Some time for questions.
But can I just say, 2 minutes? Yeah, right. Okay, sorry. I think you should give extra time for erasing. Okay. All right. Okay, so I just want to say here, before Wiles, so Faltings wrote an amazing theorem, Gert Faltings. He proved that if you have, let me say it this way, so if you have an equation like this, f of x, y, z, a homogeneous, this is a simple statement, polynomial with, let's say z coefficients. And so given it's homogeneous, you can look at the degree, let's say of degree n, and suppose it's greater than equal to 4, then there exists only a finite number of rational solutions of f of x over n equals 0. And it's a really beautiful theorem. So, for example, his result already implied Fermat's last theorem had only finitely many possible solutions. get a lot of solutions by multiplying. So maybe I should really hear primitive in some suitable sense. Sometimes it's better to say projective solutions, but so the solutions here. And the thing that I wanted to say is that if you, these things here, this f of equals 0 is defines a curve here, algebraic curve. There's x. And then if you look at x of c, then this is going to be a Riemann surface. And if you know some complex nouns, then it's associated to a G, which is a genus. And the point is that somehow there's a trichotomy. That's the last thing I want to say. Excuse me. Sorry. Trichotomy. It's like G equals 0, G equals 1, and G greater than or equal to 2. And it turns out in this domain where Falking is proved that there are only finitely many solutions. Here, something interesting happens. Either you have no solution, or you have infinitely many solutions. Here it could vary. Sometimes finitely many solutions, sometimes infinitely many. And this is kind of the thing where you have the elliptic curve they told me about. So there's a trichotomy. I don't have time, but I was going to talk about, in general, there's a conjecture of Lang which says that in this situation, in any dimension, you should have only finitely many solutions. That's one of the things I work on. So, okay.
Questions for Dinakar?
Did I go too fast? No, it's okay? All right. Yeah?
I wanted to ask, with Falking's theorem, if we knew there are only finitely many primitive rational solutions,
Yeah?
then why couldn't they just easily check all of them? If we
Oh yeah, that's good question. Because Falking's proof is not effective. So it's a completely open problem to make this proof effective. If you can do that, you'll be a professor at Harvard. You'll have a undying fame awaits you, because it's really not known. And it's very difficult. So already, people are trying to do that with special classes of equations. It's very difficult. That's right. You don't know how to make it effective because you don't know. It might take a million years to check all this. How do you know? That's the problem in number theory, is that if they are especially sparse and are only finitely many, there is no pattern. You can't say it has to go in this line. It's like, yeah. Anyway, good question. Thank you.
Other questions?
Yes?
Just to clarify, effective does or does not mean constructive proof of the solution? Or is effective more of the computability theory type
I
thing?
mean computability type, yeah.
Yeah, just to,
Right.
so what would be the definition there, if it's quick enough of a definition?
No. Okay. No, you can, so essentially what we do, at least I'm not an expert, but the way is that suppose you take the curves and so on, so you can try to give some quantity that measures the curve. Like, for example, the height, something called the Falking's height. And then you can say, anyway, so you can ask in terms of heights of points or heights of the curve, whatever. In terms of that, you can ask how far do you have to go before you get this. So that's one way. Yeah. How can you quantify the number of points? For example, the number of points bounded by h squared. H is the height. That's one way. There are other ways to do it also. So you can also instead, you can also just take the coefficients of the polynomial, then you can look at their sizes and then take the maximum of that and think of that as a height, and you can ask it again. So you have to say, you have to quantify it. Of course, I can always give you a curve where it'll take you 100 years to check the first solution. Even the current state of computers. Of course, in 10 years from now, it'll be different. But anyway. So you can only, so effective usually means that you make a quantity depending on the curve, like the height or something, and then you can ask, how far do you have to go once you measure that?
Okay.
So that's effective. It's not quite
equations for